Okay, welcome everybody. We're going to get going now. Peter is going to introduce Stefan and get going. Thanks. Go ahead, Peter.
Hello, good evening, everybody. It's a great pleasure for me to introduce Stefan Lotz to you this evening, our speaker from SANZA. I've known SANZA, Stefan, for quite a while, since he was a student at UCT doing his master's, and then as a colleague at SANZA here in Hermanus. At the moment, he is a permanent employee as a researcher, and he plays a key role in the space weather program of SANZA, doing modeling. And part of his modeling tools is the use of artificial intelligence, or what we call machine learning. And he's going to tell us tonight more about all his endeavors. And I hope everybody enjoys it. And Stefan, the floor is yours.
Okay, thank you. Okay, so as you can see, the title of my talk is a bit, how do you say, a bit of a hype and over exaggeration, as is the case with a lot of AI and machine learning stuff you've seen in popular media and popular science and in movies and things. So I thought let's just run with that. But hopefully by the end of this talk, you guys will have an idea of what we're doing, at least on our end. So this is not an exhaustive explanation of the field. We're barely going to touch the surface, and we're only going to focus on the stuff that we're busy doing now at SANZA for the next year or so. So the outline of my talk, I'll say a little bit about space physics and space weather, just because this is kind of the application field we are working in. And since you guys are the astronomy group, you might be interested in what we're doing in that sense. Then I'll talk a bit about neural networks. We'll just talk a bit about the definition and how you actually train a model like that. We'll go through a simple space physics-based example. So we'll predict I'll just show an example of where we predicted the size of the magnetosphere based on the pressure from the solar wind. And then we'll start talking about the interpretability or explainability of these models. And this is really our focus for the next year or so, with the group of the group at MUST from the Northwest University. And we'll talk a bit about this project we're currently working on. So on that note, I don't know if you guys know this, but there's a facility of Northwest University in the Faculty of Engineering that's based in Hermanus. The name is still MUST, stands for Multilingual Speech Technologies. So they started off as a sort of a spin-off of a research group that did a lot of machine translation, so automatic translation, so speech to text, and then just translation between languages, based at Northwest University at the Valdriuk campus. Somehow they moved this research group to Hermanus. I don't know how that happened, but they're still based in Hermanus. And even though the name is still connects them to speech technology, they're not doing a lot of that anymore. They are really looking at the theoretical and basic underpinnings of deep learning. I'll explain what that means exactly in the next slide. So they focus specifically on deep learning and sort of the development and theoretical underpinnings of that. And I work with them now, and I've through them now have a collaboration with or affiliate position at Northwest University. So if you didn't know, there's a bit more research and academic stuff going on in Hermanus than just SANZA and the whale unit, you know. NITHEX is the National Institute for Theoretical and Computer Science, and they are funding the project we're currently doing with MUST on the interpretability of machine learning models. That's based in Stellenbosch. So it used to be the National Institute for Theoretical Physics, but they changed their focus slightly to include a lot more math and statistics, data science, astronomy, that kind of thing. So they're now called the Institute for Theoretical and Computational Sciences, and of course SANZA As you know, we're the space agency. Our focus is on space physics research. And because of the good quality, the volume of good quality data we have going around these days, a lot of us utilize machine learning for a number of different purposes to build prediction models. Okay, so when we say space physics, let me just move this. When we say space physics, we really mean the impact it has, or we are really interested in the impact it has on technological systems. So that's sort of the application part of it, which we call space weather, and space physics is the sort of the physics underpinning of that. So the short description, as the Americans, they love little catchphrases, so they talk about sun to soil modeling. That's what they're always trying to do. So that means you look at the eruption that happens on the sun, so whether it's a coronal mass ejection or solar flare or just a high-speed stream or whatever the case may be. So from this impact or explosion or eruption or emission from the sun, we trace this plasma usually across space all the way up to the Earth's magnetic field, where these two plasmas interact, and there's a lot going on in terms of recombination and just a readjusting of plasma through waves that drain energy out of the plasma through current systems that have to be reorganized. So there's a lot going on, as you can see in this plot on the top right-hand side. There's a lot going on, but then the impact of that is really practical. So the picture I show in the bottom right here is part of a transformer, so the windings of a transformer that got burnt after a geomagnetic storm. I'm just going to play this quick video here. I just want you to get a feel for the interaction between these things. So something happens on the sun, the CME, the plasma gets ejected, it impacts the Earth's magnetic field, that gets compressed on the day side, elongated on the night side, and there's this injection of energy right into our atmosphere, and that's one of the outcomes of that is the aurora, the northern and southern lights. So this is kind of the lab we are working in. So now you can imagine if we start collecting years and years and years of data of what the sun is doing, and then what the Earth is doing, or what the Earth's magnetic field is doing on the ground, then we have a lot of data to work with, and then we can start doing some statistics. And that's where the machine learning comes in. So in the last few years, there's been so much advances in machine learning. It's really difficult to keep up. A practical example is the textbook that we use with MUST to train a new student. So every year we have a sort of a boot camp, and we slowly work through the textbook for the first 2 or 3 months of the year, just to get the new students on board. The textbook from 2016 is already out of date. So we've already upgraded to a new textbook. These things happen extremely fast, extremely quickly. And so coming with that is a lot of hype and a lot of misinformation, but we'll take that. With all the good that comes out of it, we'll take that. So the top left-hand graph or figure I have here just tries to communicate where machine learning, neural networks, and deep learning fits into this, into the bigger field of artificial intelligence. So artificial intelligence is anything where a computer helps you to make a complex prediction. So that can be like when Deep Blue and what was it, Kasparov played. That was artificial intelligence, but that was not a neural network, for example. That was just a computer that, by virtue of it being able to run very quickly through a lot of options, was able to compete with a human. So that was a sort of a brute force solution. So that fits into the broad field of artificial intelligence. Machine learning has more to do with the statistical side. So learning the most obvious, or the most likely outcome by looking at a lot of data, and you use the computer to look at a lot of data. Neural networks now is a method to achieve machine learning. So that is the thing that the structure that's plotted here on the that's shown here on the bottom left. That's what a neural network looks like. It's a bunch of nodes. So all these circles are little simple equations. The connections between them are weights, weighted connections. So these connections can be weak or strong. And I want you to note the layers. So the difference between a neural network and what these days called deep learning, that just refers to the number of layers. So because computers these days are much cheaper and much more viable to do really big simulations, we can kind of throw the kitchen sink at them and have very deep layered neural networks. And the deepness or the depth of a neural network is really something that increases its capacity. And when we say capacity, we mean ability to solve complex problems. So the bottom left-hand picture I show here is a very simple neural network. It takes handwritten digitized digits, and you feed it a digit, and it tells you whether or not it's a 1 or a 2, or well, 0, 1, 2, or say up to 9. That is the data set that this comes from is used by any and everyone. So when you're building new models, you use this MNIST data set to test your model on. So this is the sophistication of these things, where something as complex as identifying handwritten digits is used as a toy problem. So this is where we are these days with these things. Just a simple example, I just saw it on Twitter today. This is the video that's playing now is sign language being recognized automatically by a deep learning model. So this is where we are in this field. So you can imagine trying to program a computer to say, what's the signal what's the sign language signal I'm using right now? That is not something you want to solve explicitly. That is something you want to solve in a statistical sense by presenting lots and lots of data. So, okay, right. So here I'm just quickly going to divert to space physics. Oh, no. What happened here was that I inserted this slide in the wrong order. So the next slide here is just talking about space weather. It just explains why we're interested in it. The takeaway here is that these emissions from the sun has an effect on a lot of different technologies. And because we can't dictate what the sun does. Hello? Are there any questions at this stage? Can I continue?
Sorry, Stefan, I think somebody was just joining there and they had their mic on.
Okay, okay, no problem. Okay. Okay, so the point here is just, so sorry for my slide being out of order. The point here is that since we can't dictate what the sun does, we need to mitigate, and the only way we can really mitigate is to provide sort of nowcasting predictions. So what's the effect of current situations now on the specific technology that we're looking at, and then forecasting, of course. And that's where the machine learning stuff comes in. Okay, so remind yourself of this slide. So we're looking at machine learning. It's a complex thing. It works with data. So a simple illustration of what a neural network is and what we're trying to achieve here is, imagine we have a band and they're each playing their own instrument, and we have a recording of this band. So we have their album and we have the musicians. How we got to the processed album, how we got to the final product is not known. We know these sounds all went through a mixing desk, and we know what the result was because we have the LP or we have the CD in our possession. How we got there, we don't know. We don't know the settings on this mixing desk that achieved this particular sound. So that's basically what a neural network model hopes to achieve, is that given that we have the input data and we have the output data, how do we reverse engineer the model in between to achieve that output? I hope this makes sense. I was thinking about a way to simply explain what a neural network does, and I think, well, this is the best I could come up with. So the equation in the top right here just shows that in a slightly more formal way, but I'm going to reference this equation later, time and time again in the later slides. So we have data for y, we have data for x, but we don't know the function f that transforms x to y. In the same sense that we have access to the musicians and we have the final product, but we don't know what the sound engineer did to achieve that. So did he use a lot of guitar and not so much violin, or did all the musicians contribute equally? And did they contribute equally all the time, or was there times when the guitar player played a solo, or the pianist had the intro and the drummer had a solo later? So that combination and how that combination changes with time is what the model seeks to, what is the problem that we seek to solve. So when we are training a neural network, it starts with a random model. So we start with something where these weights, remember the picture with the digits I used earlier, we start with where these weights are all random. So we have input parameters, hidden nodes, and an output node. And we start with random weights. Now, in order for us to reverse engineer the symphony or this band, we start with a random selection of instruments, and we tell them each to play a little thing. And we mix that together in a random way, and then we listen to the output. And we say, oh, well, does this sound like the recorded album? No, it doesn't. And then we test that prediction. And we say, well, how much does it sound like the recorded album? No, not a lot. And then we adapt these weights, right? And we test again. How much does it sound like it now? And then we adapt the weights, test again, adapt the weights, test again, until that difference between what we expect and what we hear in the test prediction is small enough. So if we achieve something that sounds like our final version of the album, then we stop, then we have a trained network. So we start with these randomized weights, and in the end, we end with trained weights. And the clue here in these colored arrows is that there's no structure in this landscape of weights that we start with, but there is some kind of structure in the landscape of weights that we end with. And that is the thing that we want to try and utilize when we want to explain how this model works. So a simple problem from space physics. This is something I used in, when was this? I used this somewhere in a chapter where I had to explain how a neural network works in a space physics environment. So in this case, we wanted to predict what the size of the magnetosphere, so the distance from the Earth's surface to this nose of the, oops, this is wrong. Anyway, we wanted to explain what or predict what the size of the magnetosphere on the day side will be, given that we can measure the speed, so that V is W, solar wind speed, and the NP, that's the density of the protons in the solar wind. So given that we can measure N and V, can we predict what the size of the magnetosphere is going to be? Now we have a approximate solution for that. That's the equation on the top right-hand side here. So we can see that the pressure, the magnetopore's standoff distance is determined by this pressure term. Pressure is velocity squared times density. So we feed 1 year's worth of data, V and N and R, feed that into the neural network and see, can it solve this fairly complex thing, right? And now, yes, it can. And we used a fairly simple network. Where's my, what am I going to? We have this fairly simple network here. It has 2 input nodes, 1 layer of hidden nodes with 2 hidden nodes, and then just 1 output. And it achieved very good results. It could almost perfectly predict this equation. Now, but how do we interpret this? So if I didn't know what this equation was, how the hell was I going to get this from this? These are the equations that solves this neural network. And this is a simple thing. It has 2 hidden nodes. That's it. Modern models have 1 million nodes, on the order of 1 million. So how the hell are we going to, even if we can write it out like this, how on earth are we going to interpret something like this? And this is the work that we're doing with MUST this year. So this is what we are aiming to do, and there are different ways to explain what is going on in this black box. So one method we are looking at is something called feature attribution. So the specific method we're looking at here is called layer-wise propagation. So remember I said something like when we have those musicians and they play, and then we compare what they've played with the recorded album, we decided whether or not it was a good recording, right? And depending on what that recording sounded like, we adapt those weights of the network. So we adapt these connections between the weights based on what that error looks like. So now, if there's something called I must remember the name now. It's in this, so something like a reverse Taylor decomposition. I can't remember the name. But that method is used in this layer-wise propagation, where we track that error all the way back to the input. And what that tells us is, so in this case, explainable means we can point to what the causative input feature was at this time. So if you remember our band and recording studio example, can we say that it was the combination of the drummer and the guitarist that caused this part of the melody? That would be explainable in this sense. So, and something to think about is this a good enough definition of explainable? Does explainable simply mean that we can point to a certain input parameter? I don't know, it's just a question. So propagating this error back all the way to the input, we can start seeing during this training process which input feature caused these weights to change. And in that way, we can figure out, or we can say something about we can explain a little bit more about this sort of black box model. And an example here, this is one of the math students. So using that same data set, the handwritten digits data set, he showed very nicely how the network sees this example. So the pixels inside the digit got a very high but negative importance, and the digits just outside got a very high positive importance. So now we are sort of starting to see how this model thinks, so to speak, in that a 6 is something that has this shape, but also around it there must be nothing, right? I think in this case his units were flipped around. So a 9 must be something that so the pixels in this was very important to tell it that it's a 9, but also the ones just outside. And I don't show it here, but a later example shows that how it defines a 0 was that there must be nothing in this center region of the page, so to speak. So then we can really see how this model thinks, so to speak. Right. So one of the things we did, this is from 2021. I can't remember when this guy submitted. So this is one of my first students that I supervised with MUST, is to build a solar flare prediction model. Now, to tell a computer to decide whether or not which of these spots are going to cause a solar flare, that's really not a simple problem. Not even trained physicists can do that very well without error. So we trained this model to predict flare eruptions 24 hours in advance. And you can see in this case it did pretty well. It doesn't usually do this well. So 28 hours later, we saw this flare erupt. And at this time, that spot had a 90% probability of eruption. So in this case, we used this very specific shape of neural network. So one thing I didn't mention is that these things can have all kinds of different shapes, depending on what you want, what the type of problem is you want to use, you want to utilize it on. So we used TCN, temporal convolutional network, and this is a network that allows us to attribute importance to inputs when there are time delays involved. That's where the temporal part comes in. So the real output of his project was not the fact that it could predict fairly accurately. Like I said, this is a case where it worked really well. It doesn't usually work as well. But the thing that we were really interested in are these graphs at the bottom here. So what this shows are different feature attribution methods that ranks the importance of input parameters. And in the 24 hours before the eruption occurred, that's those red sections, we wanted to see which of these input features really start ramping up in importance before the flare erupts. And the nice thing is, from this, we could really see that the important features like this top left-hand one, firstly, that they start increasing in relative importance much earlier than 24 hours. So we can possibly, with a few adjustments, push this model back to predict further in advance. But the way we understand the physics currently agrees with which parameters it picked out as the important ones. And that's sort of our test. At this stage, we're not applying this to very difficult or very unsolved problems yet. We just want to see, does this model that only has data to its at its disposal, can it, when it tells us which input parameters are important, do those input parameters agree with what we know about the physics? So that's one way of doing it. So we call this feature attribution. So this means during training, look at how the weights are changed and ascribe that to a input parameter. Another way of doing things is to simply build a model that is inherently interpretable. So this is another student that I supervised with MUST, and we call this the pairwise network. So given a few inputs, we build these substructures, and within these substructures, we had what we called summary nodes, and the summary node could tell us which of these pairs, 1 and 2, 1 and 3, or 2 and 3, which of these pairs are the most important at a certain time within the within the prediction. And we applied this to a very typical problem where we measure the solar wind just before it impacts the Earth's magnetic field, and we want to predict what the effect on the ground is going to be. And there are lots of models like this in the literature. Everyone and their dog has a similar model. So we use this because we understand the physics really well. We applied this pairwise network to this problem, and it worked pretty well. We could see how the scores of the input parameters change as the storm progresses, because we understand, and that makes sense to us because we understand from the physical point of view, the beginning of a geomagnetic storm, the physical processes are very different from the main phase and the recovery phase of the storm. And we could see this jumping out from the data. Another way to build a very complex model that is somewhat interpretable is something called symbolic regression. And I don't have a cool example to show here because we're still busy applying this to our kinds of problems. But instead, so the philosophy here is, instead of starting with a big neural network with 1 million nodes, why don't we start with a bag of equations? And these candidate equations we build up according to the data. We start building with these equations. So you can see the one I'm pointing to now. So you can start fitting, so you have a little bit of data, and you can start fitting a linear equation to it and say, well, this doesn't really work very well. So let's add something. Let's add this sine term, right? And now we have something that wiggles and it fits a little bit better than a straight line. It does oscillate, but it really doesn't fit right yet. And then through iterative adaptations and a little bit of brute force, where you just test everything to your that you have to your disposal, you eventually find something that matches. The cool thing here is that now you have something that is built up out of your bag of equations. And if you choose that bag of equations well, start with fairly simple things, then eventually you have something that's either simple or at least simplifiable. So in terms of explainability, this is really sort of first prize, right? If we can write it down in an equation that's less than a page long, then we can make sense of what's going on in this phenomenon. So this is something we're looking at currently. The specific implementation we might look at is something called AI Feynman. So it uses this process, but with a few smart pre-processing steps, to build up this set of equations. And what they did in this paper that I referenced here, they solved 100 equations from the Feynman lectures. The Feynman lectures is this legendary set of lectures by Richard Feynman. Richard, right? Yeah, I think so. That was written up in a set of textbooks, volume of textbooks. But anyway, they solved 100 physics equations using a little bit of data and this method, and it worked better than the current state of the art at the time. So we want to see if we can apply this, for example, to that magnetopause distance problem I showed, because that's a really nice, fairly simple example. All right. Okay, so where are we headed with all of this? So like I mentioned, NITHEX is funding us with MUST to look at this problem. So the specific, so we got funding to be a research program within NITHEX, and the name of the research program is Machine Learning in the Sport of Theoretical and Computational Science. That's very broad, but the goal is to build novel methods for knowledge discovery in time series data. So that's a mouthful. Knowledge discovery just means explainability, like I explained it now. And then time series data means we're going to look at sequential data, something like this, not images. We're not going to ask the thing to identify whether it's a dog or a cat. And so the aim is to have something, to have a little workshop in October where we can demo this, and then the final product is supposed to be presented at the SACAIR conference in Stellenbosch in December. So that's the South African Conference for AI Research. This is where we are aiming with that, and in the specific problem we are currently working on is to build a similar model to this one, where we have solar wind data as input and some kind of measure of geomagnetic activity as the predicted parameter. The difference is now we want to do it at two different locations, Abisko in Sweden and Hermanus in South Africa. And the reason we want to do this is we want to build models that are based on the same set of input parameters, and then look at the difference in the models when we predict something at high latitude and something at low latitude, because we know the physical processes are very different. We understand how they are different. So again, we can now test what the model comes up with against our sort of prevailing physics knowledge. And we have a master student currently working on this. And something that I hope we do have time for is to do this kind of discrepancy modeling, where we say, can we build a model that will predict the difference between Abisko and Hermanus for a particular event? And this should then once again agree with what we know about the physical processes at play. Yeah, and it's something else we are also aiming at is to do data augmentation. So these, if you compare this red area in South America with this red area in Africa, these are places that are at similar geomagnetic latitudes, but the one is very well covered in terms of data and observations, and the other one isn't. So the problem here is mostly that it's either jungle or Sahara, so there's not a lot of space to put down fancy equipment. South America, it seems to be a bit easier. So this is GPS antenna coverage. And we want to see, can we apply the same methods that are used to build language models to data coverage. So one of the methods they use to build language models is something called transfer learning, and that means where you have, say you have one language that is very well documented, like let's say whatever, German, and you want to build a model for another language that is not so well documented, say Portuguese. You don't start training the Portuguese model off of its very low resource data. You start with the German model and you train that on the low volume of Portuguese data. And because languages just function similarly, that model will perform better than starting off with a clean or sort of zeroed out model. So we want to see if we can build something like this where we utilize data from a different place on Earth, but physically should work similar in terms of the physical processes. Can we use these methods to then augment data to places where there isn't a lot of real measurement? So that's the kind of stuff we are busy with currently at SANSA. I hope some of this made sense. If there's any questions, please shoot.
All right, thanks very much, Stefan. Can I start off, jump in with a question?
Sure.
There was an article on the FIS.org website, 10th of August. Title is Newly Described Solar Clock Can Precisely Predict Solar Cycle Events Years in Advance. And what this group found was that the solar clock, based on the sun's magnetic field, certain things happen at very precise intervals. Are you aware of that?
No, I think I know what you're talking about. There was a model by McIntosh.
Yes, Lehman and Scott McIntosh.
Yes,
National
that's the
Center
one.
for Atmospheric Research.
Yeah, I can't remember where they were, but yeah. So what they found, so this is a model for the solar cycle. So the solar cycle is this 11-year periodicity that the solar activity has. I don't think I have a slide about that. So the sun ebbs and flows in terms of activity in an 11-year cycle. And these cycles wax and wane in terms of their intensity. So you might have a more or less intense cycle. So for example, the one that peaked in about 2004 was fairly intense, and the one we just exited in, what was that, 2014-ish, was quite mild. And so what they found was that they used a different, or they built a new model to predict what the next solar cycle is going to be. And if we look at their current prediction versus what we're actually seeing, they are doing better than the state of the art. So that doesn't mean they can predict when the next CME is going to be. It just looks like it means that their prediction of the intensity of the current cycle is better than other models. So yeah, I do know about that. And they're looking specifically at the overlap between the cycles. So there's overlap in the polarity of the solar magnetic field. And I think the crux of their whole model was that the amount of overlap in the north, the amount of overlap in these polarities, there's a time of overlap between the end of the last cycle and the start of a new cycle. And the length of that overlap period correlates very well with the intensity of the upcoming cycle, something like that, if I remember correctly.
Yeah, what they say, the polar field reversal happens
That's the thing, yes.
Exactly 1/5 of the cycle, going from terminator to terminator. And then at 2/5 of the cycle, dark areas, polar coronal holes reform. At 3/5, a class of large and potentially dangerous solar flares occur. At 4/5, so so the length of the cycle is sort of varying, but now if the one thing happens, then they know what the length of that cycle is going to be, because each of these events happen at a certain fraction of the total event.
Okay, I didn't read it in that much detail. I think you did a bit more reading than I did. I didn't see the part about the.
Yeah, I was just wondering if this could have any sort of input on making your systems more accurate or not. What I can gather from what you've been telling us is that artificial intelligence is sort of almost like a shotgun approach. It's a huge amount of trial and errors, which with sort of I don't know if you use supercomputers or what you use, but with the modern high speed and capability of computers, you run through a massive amount of calculations and statistics and sort of find the best in the end.
That is exactly what happens. So it's I like to think about it as you are projecting your data set onto the space of all possible solutions, where all possible solutions are determined by these hidden parameters and how many of them there are. So yeah, it's definitely a shotgun approach, and that's the problem, where you have these almost unreasonable effectiveness of the model, and it works very accurately, but why it works just get lost in the details when you're working with millions of knobs. When you have millions of knobs to tune, it's difficult. So that's why there's a real push to look at the explainability. And in your example now, if instead of just presenting a model, so say we want to train a model that predicts the next solar cycle, or wants to predict let's say the occurrence rate of flares or something like that. Instead of just presenting it with the raw data, the maps of the sun, for example, we could rather hand it or we could rather hand it the polarity or the length of the terminator, or a level 1 processing of that data instead of a level 0 processing, and it should be able to train very much easier in that way. But that's only when you know what to do. When you are training a model to tell you, to drive your car, or to tell you whether this person is smiling or not, to quantify that in an equation is very difficult. And that's where these models really shine. So that's where people like I have to be careful, in that we don't discard too much of the domain knowledge and just throw the kitchen sink at the thing and see what sticks.
All right, very interesting. Anybody else got questions? Stefan?
Yeah, just to say very quickly that the explanation that Stefan has given of neural networks using that example of the music mixing, I think is the best explanation I've ever heard. Thank you.
Thanks. I was trying to explain it to myself the other day, and then
I actually had the same thought. I thought this was actually I hadn't heard of anything example like this. And it's a pretty good one.
Thanks.
Chris, you had your hand up.
Yeah. Firstly, also thanks for a very interesting talk. And likewise, I found your analogy quite useful, because although I've worked with electronics and software, it's quite complex for a large part of my life. I've always found this to be a bit of a gray area where it's sort of impenetrable, and you've shed a little bit of light there. So I wrote 2 questions. Firstly, on the subject of this explainability, are you at a point where you are able to take some of what I presume is copious volumes of years of recorded information and say, at this point, this is what the magnetosphere looked like, and so what did the sun look like at that time, and then correlate that according to the data you had? In other words, going backwards. Instead of predicting what's going to happen, take what has happened and see if it identifies the root cause.
That is not something we've done, but that is a known method of solving the problem in the reverse. The snag in this case. So let's see which slide now. This little bit of a snag is that, and that's where the time sensitivity comes in. Okay, this is the one I was looking for. So the The snag in that is just that the time delay from when the solar wind is measured to when it arrives at Earth is variable, depending on the speed of the solar wind. So that will complicate what you're saying a little bit, but not enough to not try it. So I like your suggestion. It's definitely something we should try. I haven't seen it done in this field before, but it is a legitimate method. There's something called a autoencoder as well that they use in that sense, to kind of in that way you don't have strict set of inputs and outputs. You just struggling to find the word now. The word you decompose the data set essentially into its constituent parts, and then using that you can build your model. But yeah, that's a cool idea. I'm trying to think where to apply it. What you're also kind of hinting at is almost something like a lookup table, and that's also something that has been done to some extent. So at least to classify what's happening in the solar wind. So if you look at these curves here, so if you just track this middle red one, if we know what a storm looks like. It has this kind of jump in solar wind speed, and then a gradual decrease in speed, and then it sort of calms down. So this, I'm talking about this middle. Sorry, I'm talking about the middle black graph. So you have this initial jump, and then it sort of relaxes. So what can be done, and what has been done, not very successfully because the storms are too different, is that when we see this shape in solar wind speed, we expect what we measure on the ground, and you kind of build up this lookup table. And I think from that point, if you reverse it, that would be very interesting. And it has, like I said, it has been done to some extent, especially to fill in data gaps, because the satellite data is full of gaps. And then using measurements on the ground where there's a lot less difficulty in measurements. If you know that what the magnetic field looked like at this point, you can guess what the solar wind looked like in the space. But that was for data imputation. That's for filling in gaps, not for prediction. So yeah, thanks. That's a good idea. I'll find a way, and I'll find an excuse to apply it.
Secondly, I was wondering, what kind of computers do you use for this sort of analysis? It strikes me that these days with graphics processors, which have literally thousands of computing elements that can run concurrently, it's probably a cheap way of analyzing bulk data like this.
Yeah, definitely. So the great sort of moat between that's already happened, but what's still increasing between the research done at companies like Google and Facebook versus the research done at academic institutions is that they can really build massive, grotesque models. And just because firstly, they have all the data, they have access to all the data because we all feed these websites every day. And secondly, they have the money to pay for the compute power. So there's this sort of break happening in between the kinds of research. So you can do, like, for example, building these little sort of adjusted neural networks. We can do this because we don't need a lot of data to test these guys on. But if we want to do anything near to commercial work, we'll have to use much better compute power. But we do have, even here, like it's not something we have to go overseas for. Our academic institutions do have access to good computing facilities. So we use, well, the stuff I run is usually very small because I just do little tests and the students run it. I use my laptop, sometimes a server here at SANSA. sometimes AWS, so that's the Amazon servers. The students at Northwest University, they either use their own cluster at the university or the CHPC, so Center for High Performance Computing, that's part of the CSIR. They exist specifically for this reason, for academic research. So the SKA takes up a lot of their compute time, as you can imagine.
So if I interpret what you're saying correctly, this is, let's say, from the hardware perspective, quite normal sort of processor, and replicating the algorithm to run on different data points. And I'm asking whether you can't do like a massive parallel processing to speed it up by using cheap hardware like graphics processors where they do have multiple computing elements.
That is exactly what happened. So that the cluster at Northwest, the one they're currently using is in the engineering department. There's a new one being built at the physics department, and that's exactly what they will be, a bunch of graphics cards, essentially. Same with the systems at the CHPC. It's very much GPU based. So the software we use is mostly it's called PyTorch. So that is the one that was developed by Google, I think. So they open source their entire their neural network code base. And the nice thing with that is it's to set it to work either single or multi-threaded, or to work on a CPU or GPU is a single argument. So I can have exactly the same model. I change one argument and then it runs on all the available GPUs. Or if I'm testing it on my laptop, I just set it to use a single CPU and it will do that. So the software environment is set up in such a way that it's trivial to jump between these different machines.
Absolutely marvelous. Thanks very much.
Okay.
Rick, I think Phil has had his hand up for a while.
Sorry, go ahead.
Thanks, Stefan. What a fantastic. Can you hear me?
Yes, I can.
Thanks very much. Lovely talk. What I want to ask, when a solar flare occurs, does it create disturbances in electromagnetic transmission on both sides of the Earth simultaneously, on the daytime and nighttime sides?
Okay, so a solar flare, no, that will be
way off. It was one of those early slides.
So a solar flare. Okay, so there are two things. So a solar
that slide, right. Yeah, there we go.
So a solar, there's a difference between a solar flare and a coronal mass ejection. So the solar flare is they do occur in conjunction with coronal mass ejections, but the flare is a release of electromagnetic energy. So that means speed of light. That's EM waves, traveling speed of light. That mostly, scientists we never talk in absolute. So let's say mostly or predominantly only affects the day side of the Earth. It's X-ray flux that arrives 8 minutes after the eruption. So that's speed of light. It arrives at the Earth. It charges the day side of the ionosphere, and it increases the number of charged particles. It causes problems with communications and with basically any electromagnetic signal in the ionosphere gets affected. That's a flare. The CME, the thing that you see on this video here, that's something different. So that is physical plasma, a volume of gas being erupted out of that active area. And that, because it has mass, it takes 2 to 3 days to arrive at the Earth. Now, this is maybe what you're seeing that now simultaneously, or not really simultaneously, but affects both the day and the night side. So what happens in this case with the CME, the coronal mass ejection, is that when this plasma arrives at the day side of the magnetosphere, there's day side reconnection that happens. So that means the day side of the magnetic field is kind of unlocked to this input of energetic particles, but it also sweeps over to the night side where there's night side reconnection. And then that magnetic field line sort of, in almost a slingshot action, injects this energetic plasma into the night side of the magnetosphere. And there you see that's what you see in this specific video. So it flows over, reconnects on the night side, and slingshots back in. So this won't happen simultaneously. It does take some time.
And what is the practical implication, practical importance of predicting that on Earth?
Okay, so the practical implication is, where's that? Let's go to the next slide, that one. So these are the practical implications. So yes, it affects all these different technologies, but what's the point if we can't stop it, right? So what we want to be able to tell our clients or our public or whatever is that, for example, we're doing a military operation now. Please be aware there's a geomagnetic storm going on, so your usable frequency between point A and point B will change. It won't be the normal seasonal. So when you're using HF communications, don't use the normal frequency, use this one, because you won't be able to talk. When you're doing precision farming, there's a geomagnetic storm going on, your error increases from 5 meters to 25 meters. So be careful. You're landing a plane using GPS. Be aware that the GPS error has now increased from this to that. Specifically for planes landing, because the vertical error in GPS increases much more than the horizontal error. So now, driving between here and Cape Town, following your GPS, you don't mind so much about a 20-meter inaccuracy. But when you're landing a plane and the vertical accuracy is plus minus 20 meters, it matters. So land by sight, not by GPS. So the application side or the service side of this is warning and forecast. We can't do anything about it, but you need to be aware that what you are measuring is not what you think you're measuring. When you're talking about satellites, there's things that they can do. They can switch off certain instruments to avoid anomalous charging and short circuits and that kind of thing. So all of this is born from or is dependent on accurate forecasts. And we are very far behind it compared to terrestrial, just normal weather forecasts, simply because there's not enough measurement points between here and the sun. That's the problem.
Thank you.
Okay.
Yeah, thanks.
Anybody else? Questions?
Yes, Stefan, Pierre de Villiers.
Thank you.
Very, very interesting and enjoyable talk.
Thank you.
I'd also like to compliment you on your taste of vinyl long player. My 68 model is 1968 model is still going strong. So
well done.
You've got good taste.
Right.
Some of the simple examples that you used, the role of human intuition and interpretation abilities was quite large. Now, particularly when there were a few of them. How important is the input of scientists in the efficiency of a complex process?
Sorry, you just broke up. You just broke up a bit. Just repeat. What was?
How important?
Yeah.
Is the human input or the human intuitive input into the success of the ultimate model? And does it become negligible when you're tackling really complex data sets?
Shoot, look, it would be great if we can arrive at a point where we are, looking for my slide now, arrive at a point where we can just dump data into a model and it will come up with this, right? However, the nuance in setting this model up, there's a million of what we call hyperparameters that needs to be set for a model like this to actually arrive at an answer. What you never see in news articles are all the failed models, you know. So a simple thing like if you build let me go back to that. If you build this model, this thing is, if you don't know what you're doing, it is incredibly difficult to get it to train. There's a lot of nuance happening in this procedure that needs to be set up by someone that knows what they're doing. Now, there's a lot going into making this as easy as possible, and we see it happening in, for example, we see it a lot with the biologists that we sometimes work with that work in Antarctica and Marion Island and that, where they dump data into a model, and it's a statistical model, and statistics are always tricky and it's always difficult to interpret, and they get answers out and they publish their papers and it gets published, and then someone with statistical background looks at it and it is horrendous in terms of the assumptions that was made. So I'm not disparaging anyone, I'm just saying the nuances and the factors that go into developing a model that actually arrives at an answer is very complex and not something I addressed here at all. But however, this is a lot closer than where we were a few years ago to achieve something like this on an unsolved problem, and it's been done. The article that this yellow picture was taken from, they discovered some new biological process using this model, using this method. So we are getting to the point, and that's where this word of, or this phrase of a machine scientist comes in, where you kind of have a scientist in a box. You just chuck data at the problem and you get an equation out. And once you get an equation out, then someone with the correct training can really read it. But to arrive at that point, to set up the model, to clean the data, to collect the data, to interpret the statistical underpinnings in terms of deciding how the training must be done, that is still very much up to experts. So yeah, I don't really have an answer. It's just, it is complex, and yes, there's still jobs for people like me.
I think you have answered my question. Thank you.
Okay, great.
Stefan, have we got time for another one from me quickly?
Sure.
Yeah, you mentioned satellite monitoring of agriculture as one of the things. I'm actually involved in that as one of the things in one of my day jobs.
Oh,
we had a strange event at the end of December, around about the 28th of December, 2021, where we monitor with software several parameters in vineyards, and I work from Bot River to Yamalanaada on several farms. We had an unexplainable glitch in the data in 1 week over all the areas I work, which it looked like, according to the satellite data, the vines were dead in that week, and then perfectly fine the next week again. And nothing, it wasn't explained by any of the other data that we take, soil moisture monitoring, weather station data, nothing. There was nothing unusual. And the same event over a large area. And there was also, I think, a coronal mass ejection or solar flare or something in that same week. I was just wondering if you had any sort of glitches in other satellites that you're aware of in that week? I don't have any memory of anything like that.
Not that I'm aware of right now, but I can
Might
go
not
back
be
and
under
check.
your specific sort of.
Yeah. I work with this I work on this stuff in the research sense, so I'm not monitoring it day by day. I'm not working directly with clients, but I'll definitely go and check, and I'll get back to you. I think I have your email address.
I asked the software people that run this thing. They're based in Holland. I put the question to me. I can either see there was something maybe in that CME which affected all the vineyards on the ground, which wasn't picked up by any of the other ways of monitoring it, or else they actually messed up the satellites which were taking the data so that their data was corrupted.
Yeah,
nobody ever came back to me with any kind of a.
Okay. Do you have do you have the raw data, or how do you?
Yeah, well, I've got the data for the particular farms that I monitor.
Okay. It will be cool to look at it. I guess if just a blind guess would be that there was some geomagnetic activity and the instrument got sort of fried, for lack of a better word, and then it could recover later on. I don't know which instrument it was. Was the like an infrared sensor or whatever?
Well, we work with there were several parameters that were all corrupt. All of them, moisture, the nitrogen, everything.
They could all be part of the same. I mean, they could all be measured by the same hardware.
Maybe they had in their computers, servers or whatever in Europe. Yeah. Maybe there was some glitch there, But something happened to affect everything.
Sure, something in the processing.
But it sounds like there was also a CME in that same week.
Yeah. Okay. No, that's really interesting. I'll check it tomorrow and I'll let you know. I think you sent the link to the Zoom call, right? So I think I have your email address. Okay.
Yes.
Okay. No, I'll have a look. So on the last week of 2021. I'll check what happened there. Okay. Cool.
Thanks.
Yeah. So we one of the things we're looking at is these models for atmospheric drag. So when there's an event on the sun, like a solar flare, what do you call it, SEP, energetic particle event, the density of the atmosphere increases and the low orbit satellites then feel more drag than usual. So we are working with a company we want to work with a company that predicts this stuff for satellite operators. So if you have this model of atmospheric density, then you can say how much the satellite is going to dive or not. So yeah, that's really completely within the realm of the things we do look at. So it'll be interesting.
All right, any more questions? At least you're getting a lot of questions tonight.
Yeah, it's always bad when there's no questions, because I know I didn't explain it that well, so that can't be.
All right. If there are no more questions, I'm going to wrap up and say thank you very much. It was fascinating. I'll upload this to YouTube eventually, and I'll send you the link, and you can let me know if there's anything I missed correct or something like
that. Okay, awesome. Thanks for the opportunity. It was great to have a chance to do this, and thanks for all the questions.
Okay, thanks very much. All right, good night, everybody, and thanks for attending.
Good night, everyone.
Thank you. Good night.
Thank you, Stefan. Thank you, everybody. Good night.
Thanks, Stefan.
Thank you very much.
Good night. Good night.